Hello, everyone. My name is Chao. Today, we will talk the necessary conditions in multi-server differential privacy. This is a joint work with Albert Cheu in Georgetown University. In this work, we prove some problems need exponential numbers of samples to be solved in the multi-server differential privacy. And it tells us that if we want to solve them with polynomial number of samples, we need interaction of servers or computational differential privacy. We will at first introduce the definition of differential privacy and the centralized and the decentralized models in differential privacy, and the possibilities and the impossibilities of these models. And then we will talk about our results and the techniques in the proof. So what is differential privacy? We say that people cannot know if one person is in the database by the result of differential privacy algorithm. We defined the neighboring databases X and X prime to be two databases that differ on one entry. And if a DP algorithm M is wrong on one of the two neighbors, an adversary cannot tell which one was the import. We use epsilon and delta to quantify the advantage of the adversary. The distribution of mx and mx prime should satisfy this inequality. We usually use epsilon to measure the privacy of the algorithm M, and the delta to be the tiny probability of leaking the privacy. In the centralized model, there is one server that computes the private algorithm on data, and the adversary can only view the output of the server. But the adversary could view the raw data if the server is compromised. In response, we can keep the raw data out of the server's view. So we can decentralize the privacy preservation process. In this work, we studied the model with several untrusted servers. For example, this is a two-server protocol. In this protocol, each user runs a randomizer on their data. Now, the first user generates Y11 and Y12 and sends Y11 to A1, Y12 to the A2. And the last user sends YN1 to A1 and sends YN2 to A2. The first server A1 then sends some messages to A2, and A2 computes the output. This is a non-interactive case. The A2 cannot send messages to the A1. In the interactive case, the server A2 can send messages back to A1. And in this work, we research the non-interactive case. So what can we do privately in these models? We can do the summation with low error in both of central and multi-server models. In the central model, given a 0-1 data set, we can add Laplace noise to the sum. And in the multi-server model, each user can split the data by secret sharing, then send them to different servers. And the servers now can add noise to the sum. For the parity learning, the parity function has two parameters. One is a set of index. Another is a ±1 number, b. For input x, the parity function computes b times the product of xj, where j is the index in the set L. And we know that we can learn the parity function with polynomial number of samples in the central model. And in the multi-server model, we can learn the parity function with the same samples against a computational bounded adversary. So the question is that if the adversary is computational unbounded, is it possible to learn the parity function with the same samples in both models? Our result shows that if we want to keep private when at most half of servers are compromised, we cannot learn the parity function with polynomial samples against an unbounded adversary in the non-interactive multi-server model. For the techniques, the information theoretic lower bound for parity learning has been shown in other works, such as local model, time privacy model, and shuffle model. And in this work, we show that the non-interactive multi-server protocols can be simulated by the internally private protocols with low error. We at first show that the two-server protocol can be simulated by the internally private protocol. And then we show that the multi-server protocol can be simulated by two-server protocol. We use online algorithm as a tool in our proof. The online algorithm starts from an initial state, and in each step, it receives one data and updates the state. At the end, it computes the output by the final state. The internally private online algorithm is defined as for any neighboring inputs x and x prime and integer t, the state t satisfies the differential privacy. Let's compare the two server protocol and the online protocol. For the initial state, we let all messages from the users to A1 and the messages from A1 to A2 to be the initial state. And for the input data, we let the messages from the users to A2 to be the input data. Here, the messages Y12 in the two-server protocol is the input data X1 in the online protocol. And here, the messages YN2 in two-server protocol is the input data XN in online protocol. And we let A2 to store in internal state. The challenge in our simulation is that storing two messages from one sample is not private. That is because only one server is compromised. So one user sends two messages to the two servers separately, and the adversary cannot view both of these two messages. So we can only store one message from one user in the internal state. And given a two-server protocol M1, we at first use a protocol M2 to simulate M1. But M2 requires access of the underlying distribution, but we don't know that. So it's only a thought experiment. Then we use an online protocol M3 to simulate M2. It removes the requirement by way of rejection sampling. Let's see the construction of M2 and the M3. For the initial state, it contains two parts. One is all messages from users to A1. Another is the messages from A1 to A2. And let's see how to generate messages for server 2 in M2. For example, it at first considered the distribution D conditioned on observing Y11, and then use this condition distribution to resampled X1, it used the Bayesian resampling technique, and then use X1 and Y11 to generate Y12. After receiving Y12, it deletes Y11 in the internal state. So the protocol doesn't contain the two messages from one user at the same time. It's only a thought experiment because we do not know the distribution D. So in M3, we figure out this problem. M3 at first received some samples from the distribution D, and it used the private rejection sampler to resample X, and use X and Y11 to generate Y12. After receiving Y12, it also needs to delete Y11 from the internal state. In M3, it used the rejection sampling technique here. So it doesn't need to know the underlying distribution D. It only needs some samples from the distribution D. And now we can extend the two server protocol to the multi-server protocol. We assume the servers have topological sorting. That means the servers with smaller index number can send message to the servers with larger index number, but the servers with larger index number cannot send messages to the servers with smaller index number. So we divide all servers into two groups. The first group has the servers with smaller index numbers, and the second group contains the servers with larger index number. So we can let a server A1 prime to simulate all the servers in the first group, and the A2 prime to simulate all the servers in the second group. And the messages from A1 prime to A2 prime is all the messages from the servers in the first group to the servers in the second group. So we can use the two-server protocol to simulate a multi-server protocol. And now we can use the lower bounds for the internally private protocol to get the lower bounds for the multi-server protocol. And we know some exist lower bounds on the sample complexity for the internally private protocol, such as the parity learning, the feature selection, the simple hypothesis test, and the uniformity test. And now we can know the lower bounds on the sample complexity for these tasks in the multi-server protocol. The limitation of our work is that the simulation only works for non-interactive protocols. That is because in the pan-privacy protocol, the analyst receives the data one by one in a single pass. So for the future work, we can consider the lower bounds for larger than one runs protocol, because our non-interactive protocol is a one-run protocol, but we don't know if we can have larger than one runs, what's the sample complexity of it. And we can also consider the minimum assumptions for the sample efficient computational DP, because we know that if we allowed the interactive between the servers, the computational DP protocols can learn the parity function with polynomial number of samples, but we don't know the minimal assumption for the sample efficient computational DP protocols. That's all. Thank you.